Sequences. An infinite sequence, or just a sequence, can be thought of as a list of numbers written in a definite order. The notation we use is a letter such as A with subscripts. So we can read this as A sub 1, A sub 2, A sub 3, etc. Or more commonly, we will simply call this A1, A2, A3, etc. The number A1 is the first term of the sequence, A2 is the second term, and in general, AN is the nth term. And we only deal with infinite sequences in this class. So every term AN will have a successor AN plus 1. And you can think of AN plus 1 as just the next term, right? The term after AN. And notice that for every positive integer n, there is a corresponding number AN. And so a sequence can be defined as a function f whose domain is the set of positive integers. But we usually write AN instead of f of n. This notation AN is just more convenient. Some other notation that we use, we can write the numbers A1, A2, A3, etc. separated by commas, and sometimes you'll see these curly brackets around the whole thing. Or we can simplify this by simply putting AN in these brackets. Or to give a little more detail, sometimes they will have the AN in brackets with n equals 1 to infinity off to the side. Now, unless it's otherwise stated, we always assume that n starts at 1. So if you had a sequence where you did not want to put in 1 as the first value of n, you would have to indicate that off to the side here. So as an example here, list the first 5 terms of the following sequences, and we'll do these one at a time. So the first one here says AN is equal to 1 divided by 3 to the n power plus 1. So the first term of the sequence is going to be 1 divided by 3 to the first power plus 1, and this is equal to 1/4. The second term of the sequence is 1 divided by 3 to the second power plus 1, and this is 1 over 9 plus 1, which is 1/10. The third term will be 1 over 3 to the third power plus 1, which is 1 divided by 27 plus 1, which is 1 over 28. The fourth term is 1 divided by 3 to the fourth power plus 1, which is 1 divided by 81 plus 1, which is 1 over 82. And the fifth term will be 1 divided by 3 to the fifth power plus 1, and 3 to the fifth power is 243. So this ends up being 1 over 244. And so if we were to simply list the first 5 terms of that sequence, 1/4 is the first term, 1/10 is the second term, 1 over 28 is the third term, 1 over 82 is the fourth term, and 1 over 244 is the fifth term, and this goes on indefinitely. For the next sequence here, we have AN is equal to -1 to the n power divided by 4 to the n power. So let's go ahead and list the first 5 terms here. So the first term is going to be -1 to the first power divided by 4 to the first power, and this is -1/4. The second term is -1 to the second power divided by 4 to the second power, which is +1 over 16. The third term is -1 to the third power divided by 4 to the third power, which is -1 over 64. The fourth term, -1 to the fourth power divided by 4 to the fourth power, is +1 over 256. And finally, the fifth term is -1 to the fifth power divided by 4 to the 5th power, which is negative 1 over 1024. And so the first 5 terms of this sequence are negative 1/4, 1/16, negative 1 over 64, positive 1 over 256, and negative 1 over 1024. And again, this continues indefinitely. Now, one thing you should notice is that the power of negative 1 here, negative 1 to the n power, basically resulted in an alternating of signs. So all the numerators are 1s, but they are negative 1s and positive 1s, and they alternate from term to term. And this is because a negative number to an odd power is negative, and a negative number to an even power is always positive. So that's just a note. Next, let's find the first 5 terms of this sequence here. Now, I will point out that you can see off to the side that we are starting at n equals 3. So the first term, it's maybe a little bit strange, but we're going to call the first term A3. And it is 3 squared minus 1 divided by 3 squared plus 1. And this is 8 over 10, which can be reduced to 4/5. The second term, which is called A4, and again, this can be a little bit confusing because normally we like, for example, A3 normally would be the third term. But in this case, it's the first term because n equals 3 is the first number. Thankfully, we don't do this very often. But anyway, A4 is going to be 4 squared minus 1 divided by 4 squared plus 1. And this is 16 minus 1, which is 15, over 16 plus 1, which is 17. A5 will be 5 squared minus 1 over 5 squared plus 1. This is 24 over 26, which is the same as 12/13. A6 is going to be 6 squared minus 1 divided by 6 squared plus 1. This is 35 over 37. And the fifth term, which is A7, is 7 squared minus 1 divided by 7 squared plus 1, which is 48 divided by 50. Or we can simplify this to 24 over 25. And so the first 5 terms in order are 4/5, 15 over 17, 12 over 13, 35 over 37, and 24 over 25. And finally, our last sequence, an, is 1 plus negative 1 to the n, and now we're back to normal numbering. So the first term is a1. a1, of course, corresponds to plugging in n equals 1, and so this is going to be 1 plus negative 1 to the 1, which is 1 plus negative 1, or 0. The second term is 1 plus negative 1 squared, which is 1 plus 1, which is 2. The third term is 1 plus negative 1 to the third power, which is 1 plus negative 1 again, and that is going to be 0. And you can kind of get a sense of a pattern this time. And so if you can sense a pattern, you don't always have to plug in every single value. So I can see that what's happening here is when you raise negative 1 to an odd power, you get negative 1. And when you raise negative 1 to an even power, you get positive 1. And so this pattern, 0, 2, is going to continue. So I know A4 is going to be 2, A5 is going to be 0, and this will continue indefinitely. And so the first 5 terms are 0, 2, 0, 2, 0. But in this case, it would be really easy to give as many terms as desired since it just oscillates back and forth between these numbers. In our next example, we wish to go backwards. If given a list of numbers, can we find a formula for the general term an of the sequence? And so to do this, you have to try to see patterns. So let's identify some patterns. The denominator is fairly simple. 5 is 5 to the first power. 25 is 5 to the second power. 125 is 5 to the third power. 625 is 5 to the fourth power. And yes, 3,125 is 5 to the fifth power. And so it does appear that, at least for the denominator, the nth term is going to be 5 to the n power in the denominator. And again, this is because this corresponds to n equals 1, this one to n equals 2, n equals 3, n equals 4, n equals 5. And you can see that the power of 5 corresponds precisely with the value of n. Now the numerator is actually even simpler. It's just 3, 4, 5, 6, 7. Never mind the negative temporarily here. So when you plug in a number n, such as when you plug in n equals 1, you're supposed to get 3. When you plug in n equals 2, you're supposed to get 4. N equals 3, you're supposed to get 5. So the numerator is always 2 more than the value of n. And so it does seem that the numerator should be n plus 2. And then finally, we have a positive term first, and then a negative term second, and then a positive term, and then a negative term, and then a positive term. And so it is oscillating from positive to negative, positive to negative. So what we need here is an alternating factor. And the alternating factor is either going to be negative 1 to the n, or it's going to be negative 1 to the n plus 1. Now, why do we have two possibilities? Well, let's think about it. If you start at n equals 1, when you plug n equals 1 into here, you're going to get negative 1 to the 1, which is negative 1. If you plug n equals 1 into here, you will get negative 1 to the 1 plus 1, which is negative 1 squared, which is positive 1. So if you're starting at n equals 1, and if it starts off negative, this is the factor that you would use. But if it starts off positive, this is the factor that you would use. So we would use this one if it starts negative, and we would use this one if it starts positive. And of course, ours starts with a positive 3/5. And so the alternating factor we're going to use is negative 1 to the n plus 1. Let's make a little bit more room here. And of course, you could also rewrite this as negative 1 to the n plus 1 times n plus 2 divided by 5 to the n. Either one of these formats is fine. And just as a note, this can be really challenging. Sometimes when you see lists of numbers, it's really difficult to develop a pattern. This one here isn't too bad. Now, in the next example, we just want to show that there are some sequences that don't have a simple defining equation. So, for example, we could define a sequence Pn to be the population of the world as of January 1st, in the year n. So, in other words, what was the population of the world on January 1st of the year 1? Well, I doubt we really know what that is, but certainly there was a population of the world, and that would be an integer. And then what would be the population of the world on January 1st of year 2? Well, again, that would be another number. So this is not well defined, right? It's not a formula that you can plug into, but it would definitely produce a sequence of numbers, a list of numbers. In the next example, we could let an be the digit of the nth decimal place of the number e. So what is the number e? According to my calculator, e is the number 2.718281828, etc. And so we can see that the first decimal place of e is 7. The second decimal place is 1. The third decimal place is 8. And you can see that the sequence that we have here is definitely following this pattern. Now, this sequence actually has a couple of additional decimal places that my calculator does not show. But here's the thing. Even though this is a well-defined sequence, you don't know what the next number is unless you happen to know what the next digit in the decimal expansion of the number e is. So if you had a computer that would give you many decimal places of e, you could determine the next several digits, but without that, it's kind of hard to know what the next number is going to be in that decimal expansion. However, it is a well-defined sequence. And finally, we have a very famous sequence called the Fibonacci sequence, which we like to give the designation Fn, F for Fibonacci, because it is a very famous sequence of numbers. And this is what we call a recursively defined sequence. And so what we've got here is the first number in the sequence is defined to be 1. The next number in the sequence is defined to be 1 also. After that, to get the third term onward, Fn is going to be Fn minus 1 plus Fn minus 2. So we're saying the nth term of the Fibonacci sequence is the number before it plus the number before that. So how does this sequence look? Well, again, the first term is 1. The second term is 1. To get the third term, we have to add these two terms. So 1 plus 1 is 2. To get the fourth term, we have to add the second and third term. 1 plus 2 is 3. To get the next term, 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. And you can see that we can keep doing this indefinitely. However, we don't have a formula for the nth term. So if you want to know what is the 100th term going to be, well, you don't know that until you know the 98th and 99th term, right? Once you know the 98th and 99th term, then you could add those together to get the 100th term. So this is a recursively defined sequence. We don't have an easy formula to just plug the number into to get the term of the sequence. Now, in this course, most of the time, in fact, the vast majority of the time, we will be dealing with sequences that have a well-defined formula to plug into to get the term of the sequence. I only give these as some counterexamples of different types of sequences. Sequences can also be graphed, so let's consider the following sequence. So the sequence where the nth term is defined to be n divided by n plus 1. And so if you plug in n equals 1, 2, 3, and 4, you will see that the first four terms of this sequence are 1/2, 2/3, 3/4, and 4/5. Now the question is going to arise, do we know what these terms of the sequence are getting closer to? So if I continue on with this pattern, are the numbers getting close to something? And so in this particular sequence, if you graph the number 1/2 on a number line, it will be right here. If you graph the number 2/3 on a number line, it will be right here. So this is 2/3. Let's label that. The next number in the sequence is 3/4, which is this number. The next number is 4/5. And what you start to see is that it does appear that if you keep on going, the numbers seem to be getting closer and closer to the number 1. And so this is one way to look at the terms of a sequence in a graph. Now there is another way to look at the terms of a sequence, and that is to actually graph it like you would graph a function. So for example, when n equals 1 down here, the value of the sequence is 1/2. And so this value right here on the y-axis corresponds to 1/2. When you plug in 2, you get 2/3. So this value on the y-axis would correspond to 2/3, etc. And you can see that as you plug in larger and larger values of n, the sequence values do appear to be getting closer and closer to this horizontal line, which is at 1. And so it would seem that the values of the sequence, or the terms of the sequence, are converging. They're getting closer to 1 as n gets larger and larger. And so what we're talking about here is the limit of a sequence. So the intuitive definition of a limit of a sequence is that a sequence an has the limit L, and we write the limit of an as n goes to infinity is equal to L, or we can write an approaches L as n approaches infinity if we can make the terms an as close to L as we like by taking n to be sufficiently large. If this limit exists, then we say the sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. And so if the limit exists, if it's equal to a number, then we say that the sequence converges to that number. Otherwise, we say that it diverges. So next we have a theorem which is going to help us find limits of sequences. This theorem says if the limit as x goes to infinity of the function f of x is equal to some number L, and if f of n is defined to be an when n is an integer, then the limit of the sequence an will also be L. In other words, if your sequence is defined by some function, f of x, and if the limit of f of x is L, then the limit of your sequence also has to be L. And here I have a graph to kind of illustrate this phenomenon. So if you have a function f of x, as you see here, and let's say the limit as x goes to infinity of f of x is approaching this horizontal line L, and if the sequence values are numbers that are on that function, then those sequence values also have to approach L, don't they? So this theorem will allow us to use things that we've learned in the past about limits of functions to help us find limits of sequences. And finally, before we do some examples, the limit laws for sequences are the same as the limit laws for functions. So these should all look very familiar to you. I'll read a couple of them. The limit of the sum of two sequences is the sum of the limits of the sequences, provided that the limits exist. The limit of the difference between two sequences is the difference of the limits. Constants can be factored out of limits. Limits of products is going to be a product of limits. Limits of a quotient will be the quotient of a limit as long as the denominator is not 0. The limit of something to a power is going to be the limit of that thing and then raised to the power. And we have a squeeze theorem for limits, which says that if a sequence, a squeeze theorem for sequences, and it says that if you have a sequence Bn, which is in between the sequences An and Cn, if An and Cn both go to the same number L, then Bn also has to go to L. And you can see an illustration of this one here. Notice that the limit of Cn is getting close to something, and the limit of An is getting close to the same thing. And if Bn is a sequence in between those two, then Bn is forced to the same limit, isn't it? Because it's in between. So that is the squeeze theorem for sequences. And finally, one theorem that will sometimes come in handy is that the limit of the absolute value of An, if that's equal to 0, then the limit of An itself has to be equal to 0. Let's do some examples. So in the next example, we just want to find the limit as n goes to infinity of n over n plus 1. So one way to do this, of course, is we can use techniques from the past. So remember, when you have a rational function like this, what you can do is take the numerator and the denominator and divide them all by the highest power of n in the denominator. which would just be n. And then this gives us the limit as n goes to infinity of 1 divided by 1 plus 1 over n. Using limit laws, we can now take the limit as n goes to infinity of the numerator divided by the limit as n goes to infinity of the denominator. And then one more step that we can take. We'll take the limit of the numerator, and then in the denominator, we will apply that limit to each of those terms. And now we have to use stuff that we've learned in the past. The limit of a constant is a constant. The limit of a constant is a constant. And finally, the limit as n goes to infinity of 1 over n, we know this is 0, right? Because as the denominator gets really large, this gets really small. And so we have 1 divided by 1, which is 1. Now this, of course, is not the only way to evaluate this limit. Another way to do this would be to think of the limit as x goes to infinity of x divided by x plus 1. So all I'm doing is replacing n with x, because now I'm thinking of it like a function. And now x can be anything, not just integers, but x could be any fraction or decimal as we approach infinity. Now we know that this limit is infinity divided by infinity, but this means that we can evaluate this limit by using L'Hopital's rule. And to use L'Hopital's rule, we'll take the derivative of the numerator, which is 1, and the derivative of the denominator, which is 1. And of course, 1 divided by 1 is 1. But if the limit of x divided by x plus 1 is equal to 1, then this means the limit of n divided by n plus 1 is also equal to 1. Because of the theorem that we talked about previously that said if the limit of a function is equal to something, then the limit of the sequence defined by that function has to be the same limit. So this is really nice because it basically means that we can apply things like L'Hopital's rule to limits of sequences. So in the next one here, is the sequence convergent or divergent? Again, we can use similar techniques. So I can say we have the limit as n goes to infinity, n divided by the square root of 10 plus n. Now we can apply the same technique. We can divide the top and bottom by the highest power of n. Now, the highest power of n down here is not n to the 1. It's the square root of n. So what I would need to do is divide the numerator by the square root of n and the denominator by the square root of n. And this will allow us to combine the denominator into a single radical, so 10 plus n over n. And on top, we'll just get radical n. Now from here, we can take the limit as n goes to infinity of the square root of n divided by the square root of 10 over n plus n over n, which is 1. So I'm just separating these. And then we can move the limit inside. So we have the limit as n goes to infinity of n, and then the square root of that. And in the bottom, we have the square root of the limit as n goes to infinity of 10 over n plus 1. Now, the bottom limit is going to be 1 because this goes to 0, and the limit of 1 is 1. And so we have the square root of 1, which is 1. But on top, we have infinity. And infinity divided by 1 is infinity. And so this sequence is divergent because the limit is not a real number. Next, we have the limit as n goes to infinity of the natural log of n divided by n. As n gets large, the natural log of a large number is large. And as n gets large, the denominator also gets large. And so we can apply L'Hopital's rule here. Now, technically, you're supposed to change this to the x variable, right? So you're supposed to say the limit as x goes to infinity of the natural log of x over x is equal to, by L'Hopital's rule, the limit as x goes to infinity of the derivative of the natural log of x divided by the derivative of x, which is 1. And then this clearly goes to 0 because as x gets large, this gets really small. So you're supposed to do that. However, it really isn't any different to simply take the limit as n goes to infinity and just apply the derivatives in terms of n. Now, technically, again, you're not supposed to do this. And the reason is because this is a sequence, and a sequence is not a continuous function. It's only defined for integer values. And if you have something that is not a continuous function, it is not a differentiable function, and you cannot take a derivative of a function that is not differentiable. However, the algebra is exactly the same. The only thing that you're doing is when you're taking the derivative, you're thinking in terms of n can be any real number. And then whenever you get for that limit, in this case it's 0, that means the original limit is also 0 according to our previous theorem. Next, determine whether the sequence an equals -1 to the n is convergent or divergent. So you could take the limit as n goes to infinity of -1 to the n. But if you think about it, this limit does not exist because the terms of the sequence are going to be -1, +1, -1, +1, etc. And you can see clearly as you progress in this sequence, these numbers are not getting close to any one number. It just oscillates back and forth between -1 and +1. So for example, when you plug in n equals 1, 2, 3, 4, 5, etc., you are going to get -1 and then +1, and then -1 and then +1. And it just does this. And so it's not converging, it's not getting close to something. So this sequence clearly is divergent. Now our next example, we wish to take the limit as n goes to infinity of -1 to the n power divided by n. Now, technically, you can't really do this limit because as n goes to infinity, this top number is going to oscillate between -1 and +1, and the bottom number gets bigger and bigger and bigger. But what we can do is we can say, well, what is the limit as n goes to infinity of the absolute value of this? Well, this is going to be the limit as n goes to infinity of 1 over n, because the absolute value of -1 to the n is just going to be 1. Because remember, -1 to the n just oscillates between +1 and -1. So the absolute value of that is always going to be 1. And of course, the absolute value of n is n because n is already a positive number. And we know that this is 0. Now, we had a theorem earlier that said if the limit of the absolute value of a sequence is 0, we can therefore conclude, this means therefore, we can conclude that the limit of the sequence without the absolute value also must be 0. So this limit is 0. Next, we have a theorem that's very useful. If the limit of a sequence an is L, and if the function f is continuous at L, then the limit of f of an is equal to f of L. So as an example, we have the limit as n goes to infinity of sine of pi divided by n. Now, this rule is actually very intuitive, but basically what you're going to do here is you're going to say, since sine is continuous everywhere, we can take this limit and move it inside of this function. And so this becomes sine of the limit as n goes to infinity of pi divided by n. And we know that this limit is 0 because, again, we have a constant pi on top, and n is getting larger and larger in the bottom. And a constant divided by a larger number is always going to be 0. And so we know that this limit is equal to 0 Therefore, the original limit is equal to the sine of 0, which is also 0. Next, let's discuss the convergence of the sequence an equals n factorial divided by n to the n power. This is a classic example. So let's go ahead and write down the sequence n factorial divided by n to the n power. We have a definition of n factorial here. So n factorial is 1 times 2 times 3 times all the way up to the number n. And of course, n to the n power just means n times n times n, a total of n times. So n factorial is going to be 1 times 2 times 3 times 4 times 5, etc., all the way up to n. And n to the n will be n times n times n times n times n. And there will be n of these n factors, right? Just definition of an exponent. And so this is equal to 1 over n times 2 over n times 3 over n times 4 over n, right? All the way up to n over n. And if you group all of these together, I want you to see that this product is definitely less than 1, right? This is definitely less than 1 because when you multiply a bunch of numbers that are all less than 1, the result is always less than 1. So I can say that this sequence is definitely less than 1 over n times 1, which of course is equal to 1 over n. So what we have is n factorial divided by n to the n power is always less than 1 over n, but we also know that it's always bigger than 0. But we know the limit as n goes to infinity of 1 over n is 0. And of course, the limit as n goes to infinity of 0 is 0. So both of these go to 0 as n goes to infinity. Therefore, by the squeeze theorem, the limit as n goes to infinity of n factorial divided by n to the n must also be 0. Next, we have the classic problem of finding the values of r for which the sequence r to the n power is convergent. So let's take this case by case. If r is a number bigger than positive 1, clearly the limit as n goes to infinity of r to the n is going to be infinity. And this is because if r is a number bigger than 1, when you multiply any number bigger than 1 by itself, it gets bigger and bigger and bigger. What if r is equal to 1? Well, in this case, the limit as n goes to infinity will be the limit of 1 to the n, and this is clearly equal to 1. What if r is equal to 0? Then this will be the limit as n goes to infinity of 0 to the n, which is 0. And then what if r is a number in between 0 and 1? What is the limit as n goes to infinity of a number between 0 and 1 raised to the n power? Well, this limit is 0 as well. Now, the way I can describe this to you is just think of the function y equals b to the x, an exponential function, where the base b is a number between 0 and 1. We know the graph of this function looks like this. And so it's clear that as we plug in larger and larger values for x, b to the x is approaching 0. Another way to think about this is if you have a number in between 0 and 1, such as 1/2 or something like that, when you repeatedly multiply a number less than 1 by itself, it gets smaller and smaller. Now, what do we do if r is a number in between -1 and 0? What is the limit as n goes to infinity of that? Well, we know that if we take the limit as n goes to infinity of the absolute value of r to the n, This would be the same as the limit as n goes to infinity of r to the n when r is a number in between 0 and 1. And we already know that that limit is 0. Therefore, the limit here must also be 0. So we're just using that absolute value theorem once again. Clearly, if r is equal to -1, the limit as n goes to infinity of -1 to the n is going to not exist. We talked about that earlier. And finally, if r is a number less than -1, the limit as n goes to infinity of r to the n is also going to not exist. Okay, this is because if you have a number such as -2, when you raise it to the n power, you get an increasing number, but it also oscillates back and forth between positive and negative. So for what values of r did this limit converge? Well, we got an answer here, 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 and here. So it converges when r equals 1. It converges when r equals 0. It converges if r is between 0 and 1. And it converges if r is between -1 and 0. So the answer is it will converge for all values of r less than or equal to 1 and greater than -1. And we have a summary of that here. The sequence of r to the n power is convergent if r is a number in between -1 and +1, including 1, not including -1, and it's divergent for all other values of r. In fact, the limit as n goes to infinity of r to the n is 0 if r is a number in between 1 and -1, and it's equal to 1 if r equals 1. Another definition, a sequence an is called increasing if an is less than an plus 1 for all n. So yes, if the next term is bigger than the previous term, we say the sequence is increasing. We say that it is decreasing if an is bigger than an plus 1 for all n. So yeah, if one term is bigger than the next term, and this happens for all n, then we say that it is decreasing. And a sequence is called monotonic if it is either always increasing or always decreasing. So for example, the sequence here, 3 divided by n plus 5, is decreasing because every term gets smaller, right? So what is an? an is 3 divided by n plus 5. What is an plus 1? Well, an plus 1 is what you would get when you plug n plus 1 into here. And that gives you 3 divided by n plus 1 plus 5, which is 3 divided by n plus 6. And so clearly 3 divided by n plus 5 is bigger than 3 divided by n plus 6, right? Yes, because when you divide by a larger number, you get a smaller overall number, okay? So since this is always bigger than this, an is always bigger than an plus 1, therefore we know it's decreasing. Now there is another way to show that this sequence is decreasing. Let's talk about the function f of x equals 3 divided by x plus 5, which we can write as 3 times x plus 5 to the -1 power. The derivative of this function is -3 times x plus 5 to the -2, which is -3 divided by x plus 5 squared. Notice that this is always a negative number because the top number is always negative and the bottom number is always positive. Do you remember from Calculus 1, if a derivative is always less than 0? Do you remember what that means? Yeah, it means that f of x is decreasing, right? So because the function f of x equals 3 divided by x plus 5 is decreasing, then the series with the same definition must also be decreasing. And I do believe this is a little bit easier way to show that a sequence is decreasing. So one more time here, let's show that the sequence an here is decreasing. So to do this, I'm going to define a function f of x to be x divided by x squared plus 1. Let's take the derivative of that function. The derivative is the bottom function multiplied by the derivative of the top minus the top function multiplied by the derivative of the bottom divided by the bottom function squared. This is x squared plus 1 minus 2x squared divided by x squared plus 1 squared. And this is 1 minus x squared divided by x squared plus 1 squared. Now notice that the bottom number is always positive, no matter what you plug in for x. And the top number, 1 minus x squared, is going to be negative as soon as you plug in a number x that is bigger than 1. So this is going to be less than 0 if x is bigger than 1. And so since the derivative is essentially always less than 0, it's always negative, this means that f of x is decreasing. And if f of x is decreasing, then an, which has the same definition as f of x, is also decreasing. Next definition, a sequence an is what we say bounded above if there is a number capital M such that the sequence is always less than or equal to that number. And it is bounded below if there is a number lowercase m such that the sequence is always larger than or equal to that smaller number. If a sequence is bounded above and below, it is called a bounded sequence. Now, what this basically means, think about in terms of a graph. A bounded sequence is a sequence that does not go to infinity and does not go to negative infinity. And so you have to have a line that it never rises above and a line that it never goes below. And so your sequence can do anything it wants to do within these lines, but it cannot go above or below these lines. So it might approach the line below here, like this, or your sequence might approach the line above here, but it cannot go off to infinity or down to negative infinity. So a bounded sequence is basically a sequence that is always in between two finite numbers. And this brings us to our final theorem. This theorem is called the monotonic sequence theorem. And it says, quite simply, every bounded monotonic sequence is always convergent. So for example, if you have a sequence that is increasing, it is monotonic, right? Monotonic means that it is always decreasing or increasing. In this case, we can see the sequence is increasing. So if it's always increasing, but it's bounded, right? That means it can't go above some number. So if it's always increasing, but it can't go above a certain number, it has to converge, doesn't it? Because it's not allowed to go down, because then it wouldn't always be increasing. And it can't go beyond this line, because then it wouldn't be bounded. So if you have a function or a sequence that is bounded above and below, and it's always increasing or always decreasing, it has to converge. And that concludes this very long video lesson, and you deserve a reward if you watched it all the way to the end.